Welcome to the Journey Chez Chem. Well, another fun-filled day of chemistry, and I know that you are getting used to the idea of putting those two problems in your composition notebook and doing the problems to the best of your ability. Well, let's do it again, and I'll see you in a moment. Number 1 asks for the complete electron configurations. And for this, I need the diagonal rule. So I draw my energy levels with a diagonal line through them so that I can follow until I get to the number of electrons that I need. Well, copper has atomic number 29. Therefore, it has 29 protons and 29 electrons in the neutral atom. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1, 3d10. And we discussed how in the D block we have two exceptions where we think that we would have S2d9, S2d9. So we would have the two s electrons, and we have 5 d orbitals, and these are called orbital filling diagrams, and we fill 1, 2, 3, 4, 5, and then we go back and fill 6, 7, 8, 9. That would be D9. However, in reality, what happens is that we get S1 and D10. We have 1 s electron, and we get 10 in the d orbitals. And that is a more balanced arrangement and has lower energy. And therefore, that is the electron configuration for that column. And for copper then, we have 4s1 and 3d10. Then sodium has atomic number 11. 11 protons, 11 electrons in the neutral atom. 1s2, 2s2, 2p6, and 3s1. 2, 4, 10, and 11. And if I go above for the copper and I counted out the 29, 2, 4, 10, 12, 18, 20, 19, and then 10 is 29. Chlorine has atomic number 17. It has 17 protons and 17 electrons in the neutral atom. And therefore we go 1s2, 2s2, 2p6, 3s2, and 3p5. And we add those numbers up, we come up with 17. 2, 4, 10, 12, and 17 electrons. Helium is an easy one. It has atomic number 2, so it just goes 1s2. And the reason that it is a noble gas, and in the column of the noble gases, you'll recall that we had the periodic chart that looked like this, and we had helium that was here, 1s2, and the rest of them were s2p6, because this makes the first energy level complete. When I look at my diagonal rule, I can see the 1s2 is a complete energy level, and therefore it is very low energy and is considered a noble gas. And that's how you do number 1. Number 2 asks for a variety of different things. First of all, it asks for the dot diagrams. Well, I need to know the ending electron configuration. That's what's most helpful for me to know how many dots. Well, when I look at copper, I see that it ends in S1 and D10. And the dots are only the S and the P as in Paul electrons. And therefore, copper will only have 1 dot. Now, its oxidation numbers or charges vary, so we don't really have a definitive answer for that. Technically, it would be +1 or +2, but that is not something that we need to know. And therefore, don't worry about that part. And however, we do also need to know the family that it's in, and this is a transition metal. Then sodium ends in S1. The highest energy level is the third energy level, and I have an S1. And therefore, sodium will have 1 dot. Its oxidation number is +1. And it is a alkali metal, is its family in that first column. Chlorine ends in S2P5, and therefore it has 7 dots. It has an oxidation number of -1, and it is a halogen, is its family name. Helium ends in S2, and therefore helium has 2 dots. It has a 0 oxidation number, and it is a noble gas, or inert. And that's how we answer number 2. Now get out that blank periodic chart and we can take a few more notes today. Now let's take a few more notes on our blank periodic chart. Although I know it's not blank anymore because we've been taking a little bit of notes at a time and adding it to that, so we have lots of information. This is one of the final things that we need to discuss. Well, we have 3 terms that need to be defined. Ionization energy is the energy required to remove the outermost electron from an atom. Electron affinity is the attraction an atom has for an electron, and I have an affinity for chocolate. And electronegativity is the ability of an atom in a compound to attract an electron to itself. These first 2 are experimentally determined numbers. They are actually measured values. And electronegativity is a man-made scale by Linus Pauling. And because these are measured values, we found that there's a couple of exceptions in there, and we need to determine why that is. Well, in general, all 3 of those increase as you move from left to right. And the reason that they increase from left to right, because as we are going across a period, we are increasing the number of protons. We are increasing the nuclear charge. And that is why it increases from left to right, because it is holding on more tightly to those electrons. And therefore, the increase is from left to right. As we move down the group, the ionization energy, electronegativity, and electron affinity decrease, because as we go down, we are increasing the number of energy levels. And let's look at how that works. Well, on the very first energy level, we only have one area where we find those electrons. And in the center, we have the nucleus where the protons are, and we have that positive charge, and therefore the electron is out there. Well, as we move down, we get more and more and more and more energy levels, and therefore the electron is much further away from that nuclear charge. And this is like when we are very young and we live at home. Our parents are our nucleus. They have lots of control. As we get older and we move away from our parents, the parents have less control. And we call this the shielding effect. The electrons are shielded from the nuclear charge because they're so far away as we move down the group. And therefore, the reason that the ionization energy, electron affinity, and electronegativity decrease as we go down is called the shielding effect. And the reason that it increases from left to right is because of a greater nuclear charge. It's very important that we read the question as is asked very carefully, because the nuclear charge increases from left to right, but if we were moving in the opposite direction, it would decrease. It's very important always to read the question. Now, we also have two exceptions that occur for ionization energy and electron affinity only. It does not occur for electronegativity because it's a man-made scale, and those exceptions were taken out. Well, I can thank a student for helping me with a way for students to remember what the exceptions are, and it is called Ben. And the first exception occurs with beryllium. Well, beryllium has an ending electron configuration of s2. It looks like this. Boron has an ending electron configuration of this. Now, when I do the orbital filling diagrams, it's important that you show each line because there are 3 p orbitals. And even though there's no electron in there, I still must show it. It's just like when I'm not home, I'm not there, but my house is still there, so I still have to show it. Well, it's much easier to remove this electron than it is one from here. This has less attraction for an electron than this one here. And in general, when we look at it, we see that it goes 1, 2, 3, 4, 5, 6, 7, 8. That would be increasing. And we see that there are exceptions, 1, 3, 2, 4, 6, 5, 7, 8. And this is where the exceptions occur. And we discuss the first exception for beryllium. Then the next exception is for the nitrogen. Well, nitrogen has a configuration of S2P3. And oxygen is S2P4. And when there is one electron in each one of the p orbitals and they're all spinning the same direction, that's lower energy. And therefore, it is not going to want to lose one of those electrons as much as the oxygen. And you'll notice that the exception is only for the one right next to it, not as we continue on. And the attraction that the atom has for an electron is not as great for the nitrogen as it is for the oxygen. And those are the two exceptions. The Ben, where the beryllium column and the nitrogen group. And the reasons why are given as nuclear charge as we move across and shielding effect as we move down. Those 3 trends follow the same pattern, and that's why we keep them together. The next one that we're going to discuss, which is atomic size, is the opposite of this trend, and that's why I try to keep it separate so that we understand and we don't get them mixed up. Well, I'll be right back to talk about atomic size. The atomic size follows the snowman. We use the snowman to remind us how it goes. Well, atoms are, in general, circular, or actually they should be spheres because they're 3-dimensional. Well, we measure the size by the radius that goes in the middle of the sphere to the edge. And we remember how this trend goes because it looks like a snowman. Well, snowmen have little heads and big bodies. And this snowman always falls over in this direction. And therefore, we know as we go down a group, we get more and more energy levels. As we get more energy levels, we have more electrons, and therefore the size gets much larger. Then, as we go across, as we just discussed, the nuclear charge increases. Well, as the number of protons increases, it holds on more tightly to those electrons and pulls them in. There are no exceptions to this. The size increases as it goes down and decreases as it goes across. And it's very important to keep this trend separate from the trend that we just discussed about ionization energy, electron affinity, and electronegativity. And there you have it. Well, that's some notes today, and you get to practice this evening. And I can't wait to see you tomorrow. Bye.